This is the second lecture on moment of inertia. In the first lecture, we have developed the concept of moment of inertia. We have discussed the perpendicular and parallel axis theorem. What will be the unit of moment of inertia, that has been discussed, and a simple numerical on how to calculate the moment of inertia of a rectangular lamina. Now again we will start from where we have left. So this was the problem. This was the rectangular lamina of width v and height h, and we have calculated what will be the moment of inertia of that rectangular lamina about the centroidal x-axis, and we got this expression that it is bh cube by 12. And due to symmetry, we have also discussed this is the moment of inertia about the centroidal y-axis, that is simply hp cube by 12. Now, as for example, if this is your lamina, and this is the centroidal x-axis, and this is your centroidal y-axis. That means this is the centroid. The axes passing through the centroid are known as centroidal axes. So from the previous calculation, we know that the moment of inertia about the centroidal x-axis is ph cube by 12. Now we will use the parallel axis theorem. If you want to calculate what will be the moment of inertia of this laminar about this axis, say this axis is AA axis. So if I want to calculate what will be the moment of inertia about this AA axis, which is parallel to the centroidal x-axis, then using parallel axis theorem, we can say it will be the moment of inertia about the centroidal x-axis plus the area of this lamina, that is b into h into square of the distance between these two axes, and this distance is h by 2, so square of that. So this ixs is bh cube by 12, we know, and this is coming as bh cube by 4. So bh cube by 4. So how much it is coming? It is bh cube by 3. So from this we can conclude that the moment of inertia about the centroidal axis is less than the moment of inertia about the axis which is a bit away from the center. So you will get the least moment of inertia about the centroidal axis. Okay. Now simply we will calculate another problem, that is for triangle. Say this is a triangle, any triangle. This is our x-axis and this is the y-axis. Say this base is b and this height say h, and we want to calculate what will be the moment of inertia about this x-axis. So we want to calculate that one. So the formulation is simple, just like previous one. Take one elemental area, a small elemental area which is at a distance y from x-axis, and the width of it is dy. Okay, as it is a very small area, you can think it as a rectangle. So what will be the area of this rectangle? So this length, say this length is x into dy. So this is the area of this rectangle. Now what is x? If we want to calculate what is x, then from similar triangle we can say, let me write it down, say O A B. This is the outer triangle, and this one O A dash B dash, the inner triangle, the smaller one. So we can say the base of the outer triangle B, this base, divided by the base of the inner triangle is equal to the height of the outer triangle divided by the height of the inner triangle. What is the height of the inner triangle? This much is y and total is h, so h minus y. So from that we can calculate x is equal to b by h into h minus y. Clear? So now the formulation of Ixx is simply y squared dA over the whole area. So just write dA as x into dy, x into dy. Now we can't write x here because the integration will be with respect to y. So we need to write the expression of x with respect to y. So what is that? We know from this is b by h to h minus y dy. What is the limit of x? Sorry, limit of y. Y starts from 0 and ends at h. So from 0 to h. We should write limit here also. So b by h is constant. So within integration, it is h y square minus y cube. So that is your dy. Okay. So b by h coming as h y cube by 3, 0 to h, minus y to the power 4 by 4, 0 to h. So how much is that? B by h. So it is coming at h to the power 4 by 3 minus h to the power 4 by 4. So b by h, 4 minus 3, that is only h to the power 4 by 12, and it is coming as b h cube by 12. So this is the moment of inertia of a triangle about the axis which is passing through its base, that is this x-axis. Now, if we want to calculate what will be the moment of inertia about the centroidal axis of this triangle, mean I know this is the triangle and the centroid lies here at an height h by 3 from its base, because the total height is h. Clear? So I know the moment of inertia about this x-axis, and that is Ixx is equal to bh cube by 12. I want to know what will be the moment of inertia about the centroidal x-axis. So all I need to do is to mark this one. So that will be bh cube by 12. Now as you are moving towards the centroidal axis, the moment of inertia will decrease. Okay, just like the previous case which we have done in rectangular lamina. If you know the moment of inertia of the centroidal axis, then this will be minus area of the triangle, that is half into base into height into square of the distance between these two axes. So that is coming as bh cube by 12 minus bh cube 918 is coming as 18. So if you do this, you will get bh cube by 36. Now, is that portion is clear? I think, because it is coming as that Ixx is basically Ia into area into h by 3 square. So ICC is Ixx minus this term. So that is why I have written minus here. Okay. I think it is clear. Now we are moving to the hollow section. Suppose the hollow rectangular section. Say there is one rectangle of width b and height h, and there is another rectangle of width b and height h inside of it. So this portion is hollow. It looks like this one in a three-dimensional manner. Okay, this portion is hollow. Nothing is there. So this is the portion area which is withstanding the stresses. So if I want to calculate what will be the moment of inertia of this hollow section about the centroidal x-axis, it will be simply moment of inertia of the outer one, that is b h cube by 12 minus moment of inertia of the inner one. So you are subtracting the total hollow section. So this will be this one. Now all these were in Cartesian coordinate. So now we will develop what will be the moment of inertia of a circular section. That is our circle. It is a solid circle. Okay. So what we are doing, we want to find out the moment of inertia about this diametral axes. So first of all, we will calculate what will be the moment of inertia about an axis which is perpendicular to the plane of this paper, that is z axis. So for that, we are considering one elemental annular section. Elemental annular section at a distance r of width dr. Okay. So what will be izz? So that will be integration r square dA. R is the distance from the axis. This is the axis which is passing through this point and perpendicular to the plane of the paper. So this is. Now what is dA? dA can be written as, think what is this perimeter of this inner circle. It is 2 pi r. Basically I am opening this up. This will look like this one. This width is dr. And what is the length of this? This is the perimeter of this circle, 2 pi r. So 2 pi r into dr is basically the area of this element. So that is coming as r square to 2 pi r dr. Now what is the limit of r? The r is 0 here, and here say the radius of the outer circle is capital R. So the limit is 0 to this one. So 2 pi comes outside. So we are left with this integration r cube dr. So that is coming as r to the power 4 by 4, 0 to r. So we are getting pi r to the power 4 by 2. Or you can write it in terms of diameter also. So if you write it in terms of diameter, r is basically d by 2. So d to the power 4 by 2, where d is dia. So pi d to the power 4 by 64. That is the moment of inertia of this circle about this axis z. Not about x, not about y. But we know from perpendicular axis theorem that the summation of these two moment of inertia is equal to this one. Now, what is the moment of inertia about this axis? Will be same as the moment of inertia about this axis. The moment of inertia about axis x and the moment of inertia about axis y is same. So we can write 2 is equal to 2 of ix is equal to izz. So that is, I think I have done something wrong here. This is, sorry, it's my fault. 2 to the power 4 is basically 16. Okay, so this will come as 32. Okay, so this is coming as pi to the power 4 by 32. So ixx equal to pi to the power 4 by 64. Now it's right. Yeah. So pi to the power 4 by 64, and this is equal to this one. So now we know that for a circle, the moment of inertia about the diametral x-axis is pi d to the power 4 by 64, and for diametral y-axis it is also pi d to the power 4 by 64. Now if it is a hollow circle, say if it is a hollow circle, I want to find out what will be the moment of inertia of this circle about axis x. Now this, say this inner diameter is small d and this outer diameter is capital D. So it will be simply Ix is equal to pi d to the power 464 minus pi d to the power 4 by 64. Okay, so I shall stop now. So in this brief lecture, we have calculated the moment of inertia of a triangle and the moment of inertia of a circle. Also, what will be the moment of inertia of a hollow rectangular section and for a circular hollow section. Now in the same manner, I am leaving upon you find out what will be the moment of inertia of a quarter circle about, say, this axis. Say this radius is r, and what will be the moment of inertia of the semicircle about the axis of x. Okay, its radius is same as r. So these are the problems which you need to do. In next class, we will deal with the composite sections, but everyone must answer these two first.